Building a model maglev train.
Short for a magnetic levitation train, a maglev train is a type of train that uses superconducting magnets with like poles facing one another on the track and the bottom of the train to make it float. They are generally very fast-moving trains as there is not much friction generated from the tracks.
So we decided to construct our model maglev train using cardboard, 58 ferrite ring magnets, a lot of hot glue, 6 wooden planks, and a section of acrylic sheet. Later, we took some measurements and collected data in order to determine changes in energy. As you can see, there are magnets all along the bottom of the train and the track, and pretty much all of the components were fixed together with hot glue. Maglev trains are able to move really fast due to their lack of friction between the train and the track, and we wanted to use the idea of conservation of energy in order to show this. So in order to test this, we set our maglev track up on a slope with a height of 0.1 meters and recorded its final velocity using a meter stick and a timer.
Our project covered 9 physics concepts in total. 3 of them are outside class topics, which are polarity, magnetic fields, and magnetic forces, while the 6 familiar concepts are gravitational forces, free body diagrams, systems, kinetic energy, potential energy, and friction.
To start off, we can't understand magnets without understanding polarity. A magnet has 2 poles, a north and a south. Generally, the south poles are defined as positive and the north poles are defined as negative. Polarity plays a major role in our project as the direction of the poles of the magnets on the track and the direction of the poles of the magnets connected to the bottom of the train itself are the same facing each other. Since like poles repel and opposite poles attract according to the law of magnetism, the train can hover above the track this way. We also had to consider the magnetic fields of our magnets. The definition of a magnetic field is the area surrounding a magnetic body that carries an electric current within which the magnetic forces act. In simpler terms, the strength of a magnetic field determines how strong it repels or attracts to other magnets. When considering what materials to use, we had to ensure the magnets were strong enough to hold the weight of the train off the track, but still be easy to handle and have manageable strength. After testing a bunch of different magnets, we eventually landed on using ferrite or ceramic magnets for their low cost and suitable field strength.
Now let's get on to magnetic forces. A magnetic force is a consequence of electromagnetic force and caused by the motion of charges. As we know, objects with the same direction of charge will attract, and those with opposite direction of charge will repel. You can find the magnetic force using the Lorentz force law, where Q is a charge, V is a velocity, and B is a magnetic field. When the angle between the velocity and magnetic field vector is less than 180 degrees, you multiply your equation by the sine of the angle. What other force is acting on our maglev train? Well, we've got gravitational force. The gravitational field strength in Los Gatos is 9.79 meters per second squared. The universal force of attraction pulls 2 objects with mass together. In this case, they are the train and the Earth. Since the train's mass is much less than that of the Earth, only the train is set in motion because of the force of gravity. Let's take a look at the free body diagram for our train. When the train is stationary on a flat surface, the force of gravity is equal to the magnetic force which opposes it. On an inclined plane, the force of gravity has a y component equal to the magnetic force, since it does not move up and down, and it has an x component that accelerates the train down the slope. When examining energy, we must consider the system. As a reminder, an open system allows both matter and energy to cross its boundaries, while a closed system only allows energy to enter and exit. In the train track system, energy is conserved since friction between the walls and the train is absorbed by the cardboard for the most part. However, in the train-earth system, energy is not conserved since the track is not part of the system.
Now let's observe the system's potential energy, specifically the energy stored in an object from its relative position, which is also known as the gravitational potential energy. We can assume that energy is mostly conserved in our scenario, besides minimal energy loss as friction. So, using this concept of the conservation of energy, we can set the initial energy equal to the final energy, which also means we can set the initial gravitational potential energy equal to the final kinetic energy, since there's very minimal friction. We can use UG equals mgh, since that's the equation for gravitational potential energy, and multiply the height of the track, which was 0.1 meters, the gravitational field strength in Los Gatos, which is about 9.79 meters per second squared, and the mass of the train itself, which is about 0.26 kilograms, to get 0.25 joules for our gravitational potential energy before the train is released. The next type of energy we measured is kinetic energy, which is defined as the energy of motion. Here we're only going to observe translational kinetic energy, which is represented by the equation of 1/2 mass times velocity squared. The train begins at a certain height and slides down to a height of 0 meters at the end, so most of the potential energy will have been transferred into kinetic energy at this point. We found the final velocity of the train using video analysis and obtained 1.25 meters per second. This is squared and multiplied by 1/2 of the mass, and then our calculated kinetic energy ended up being 0.2 joules, which is also the total final energy of the system, not including friction. So after solving for both the potential gravitational energy and the kinetic energy, we were able to plug them into this equation and prove that the energy in the train-Earth system was mostly conserved, as only about 0.05 joules of it left the system as a form of friction, which will be talked about in the next slide. However, this does show how maglev trains are able to go as fast as they do. They experience little to no friction with the track itself, since it essentially hovers and therefore has more kinetic energy, and in turn more velocity than normal trains might have.
Now let's discuss friction in more detail. Friction resists the sliding or rolling of one object over another. Originally, we planned on the track walls being completely acrylic, which would reduce the energy lost as heat. After all, the coefficient of kinetic friction is smaller between acrylic and cardboard than cardboard on cardboard. Recall the equation for force of friction, where the coefficient of kinetic friction is equal to force of friction over normal force. If we assume the normal force is constant, and more friction is created through sliding cardboard on cardboard, which is evident through sound and decreased train speed, then mu will be greater. We had a lot of fun putting this project together, despite the many mishaps, tribulations, and minor injuries sustained from hot gluing ourselves. Thanks for watching.